So let's say we want to find the area under a velocity curve because we want to compute distance traveled. But the velocity curve, whose area we don't want to find underneath, doesn't happen to match up to any geometric shapes that we know. Here's our next best option. It's to approximate the area under the curve. So here I have a function, my velocity function is 1/8 t squared plus 1. We know from our experience that that's parabolic. So there's no geometry formula we know for finding the area under a parabola. So we're going to split this area up into a bunch of different rectangles and use rectangles to approximate the area. So you can see here what we've drawn. We took this interval that we care about, which is 0 to 4, and we're just deciding, sort of arbitrarily, to split this up into 4 subintervals, so 4 rectangles. And like I say in your notes, you have 2 decisions to make. Number 1 is, how many rectangles do you want to use? Your answer comes from trying to find a balance between how much math you want to do and how accurate you want your answer to be. So the more rectangles you use, the closer your answer will be to the real value, but the more math you're going to have to do. The second thing we're going to have to decide is these rectangles. How are we going to decide how tall to draw them? Because obviously a rectangle isn't going to meet this curve, this parabola curve, flush. So there are 3 common options. One is to have the rectangles touch the curve at their left endpoint. So see, this first rectangle covers the t values from 0 to 1. So 0 is the left side of that interval. 0. Where does it touch? Where does the rectangle touch the curve? It's at the place where time is 0. So you can see up here, that's where I have the height of my rectangle. Here's the height of my second rectangle. The second rectangle covers t values from 1 to 2. So the left side of that interval is 1. I'm going to use essentially the output value, in this case the v value, or sometimes the y value, where the input is 1. So you can see that's how I continue. My third rectangle touches here at 2. My fourth rectangle touches here at time equals 3. Now all I have to do, I can see that my answer is not going to be an exact answer because I've got these spaces in here. But I can add up the areas of these rectangles and find an approximation for the area under the curve from 0 to 4. In this case, to approximate the distance traveled between time 0 and time 4. So how do you find the area of a rectangle? Well, that's the base times the height. Remember, the base is going to be a difference between 2 input values. Here, the base of each of these rectangles happens to be 1. And then the height here, the height of this first rectangle is whatever you get when you plug 0 in to the v function, which is 1. This is 1 and 1/8. You can see I have a table of values here. 1 and 1/2, 2 and 1/8. So I'm going to multiply base times height, base times height, base times height, base times height, add the 4 areas together. This is the proximate area. So this is the proximate distance traveled from time t equals 0 to t equals 4. Instead, I could have drawn my rectangles so that they touch at the right end of the interval. So here the first rectangle covers from 0 to 1. So 1 is the right-hand side of that interval, and I use the height of the graph when time equals 1 to choose the height of my rectangle. So here I have 4 different rectangles. I can see each one of these is a little bit too big, so I know my answer won't be exact. But if I add up the areas of those 4 rectangles, I get 7.75. Again, an approximation for distance traveled. One more. You could have the rectangles touch at their midpoint. So the middle of this interval from 0 to 1, the middle is 0.5. So I use the height of the rectangle. I use the curve value when time is 0.5. And then here when time is 0.15. And I can again add up the 4 areas of the 4 rectangles, and I get an approximation for the area under the curve.